Good morning, everyone, and a warm welcome to the inauguration of the Gyan course on combustion theory and application. It's an honor to host this prestigious program, which aims to foster global collaboration and knowledge sharing. We are honored to have among us today Chief Guest Professor Sukumar Nandi, Dean of Administration, IIT Guwahati, foreign expert Professor Detlef Marcus, Head of Department, PTB, Braunschweig, Germany. Professor Samantha Hajarika, Head of Department of Mechanical Engineering, IIT Guwahati. Professor T. Venkatesh Bharat, Local Coordinator of Gyan and Head Center for Education and Technology, IIT Guwahati. Professor Niranjan Sahu, Course Coordinator of the Gyan course and Faculty in the Department of Mechanical Engineering, IIT Guwahati. I request all the dignitaries to please come on the dais and have their seats. Please, sir. As we begin this academic journey, let us take a moment to seek the blessings of the divine. I request all our honorable guests on the dais to proceed towards the lamp for lighting the lamp, symbolizing the illumination, knowledge and wisdom. Please, sir. Thank you all. Kindly have your seats. The Gyan course on combustion theory and application is a timely program designed to provide an in-depth understanding of the course. Course coordinator Professor Niranjan Sahu and foreign faculty Professor Detlef Marcus will share their knowledge and experience, ensuring an engaging and interactive learning experience. Now I request Professor Sukumar Nandi, Dean of Administration, IIT Guwahati, to felicitate foreign expert of today's Gyan course, Professor Detlef Marcus, with a traditional gamosa and a memento. Please, sir. Thank you, sir. May I now request Professor Niranjan Sahu, Course Coordinator of the Gyan course, Combustion Theory and Application, to deliver an inaugural address. Please, sir.
Very good morning to all of you. Dignitaries in the dais, Professor Nandi, Professor T. Bharat, Head CET, Professor Hajarika from Mechanical Engineering, and of course we both, Professor Marcus and myself. So it's a great privilege for me to announce this course, which is being delivered through our Gyan portal on combustion theory and applications. So let me explain about the background or how we evolved about this course so far. So basically a team from PTV visited to our campus 2 years ago, and they were looking at the exploring the potential of renewable energy and other energy resources which can substitute the conventional fossil fuels. Through this interaction, we had a team from industry participations from the northeast regions, oil industries. So during that time, the PTB team, along with Professor Marcus, visited to our campus, and we had one fruitful discussion during that time. And from then onwards, we started discussions of how we can make it a next generation course for particularly for the young and budding engineers, students who can make this concept be aware of. So the word combustion is derived from the primitive eras where we have simple wood combustions. But during that point of time, there is nothing the world called pollutions or any kind of climate change, and this combustion, in fact, was evolved few years ago as a fossil fuel combustions over last 100 years. But nowadays you have come to a stage that conventional fossil fuel combustion is no way reliable, is no way it has a potential to sustain for the future. So we have to come up some new alternatives that can cater the next generations. So through this concept, the word decarbonization, green combustions comes into pictures. So taking into those accounts, we try to initiate at the grassroots level for the next generation scientists, engineers, academicians to make the things aware that conventional technology of combustion is no longer valid. We have to look for the alternatives in the form of green energy. So this is the viewpoint or global aspects of how the course was evolved. So down the line we'll have variety of lectures. So basically our course structure is designed in two aspects, like fundamental theory of combustions, which are normally available in the classical textbooks, and but at the same time, and we also had designed some kind of measurement methodologies of combustion diagnostics, explosions, and where our foreign collaborator Professor Marcus will take a key part in delivering those lectures. So in total, entire benefit of this course will be in the audience of mechanical energy, energy engineering, chemical science and technology. All these groups of people, will get benefited. So the course is designed for 2 weeks, starting from today, 25th November to 6th December. So in this course, we have planned quite a significant number of lectures, and of course, every day we have one tutorial sessions where participants or students, they can share knowledge. In fact, we are planning to have similar kind of presentations from their side, so that always there will be interactive sessions. So with this note, I conclude. I hope you will enjoy the stay and enjoy this course, and thank you for your attention.
Thank you, sir, for the details about the course. May I now request Professor T.V. Bharat, Program Coordinator and Head Center for Educational Technology, to deliver a brief about the program and the activities of the center. Please, sir.
Thank you. I'm thrilled to be here today to participate in the inauguration of first GYAN program of Phase 4. I join with my distinguished colleagues, Professor Nandi, Dean of Administration, Professor Shyamantika Hazarika, Head of the Mechanical Engineering, Professor Sahu, the PA of this particular program, and also we formally welcome Professor Marcus to IIT Guwahati and this particular GYAN program. And this is a very auspicious day to inaugurate the first GYAN program, and they are very highly competitive in nature. So you must have seen now from the address of Professor Sahu that there's a lot of homework that has been done. 3 years of hard work, there's visits that happened from there to PTB to here, and there's a lot of discussion that took place, and industrial involvement. All such things have happened that speaks the success of this particular course itself. Highly competitive. We submitted around 20 GYAN programs from IIT Guwahati, and 10 have been sanctioned so far, and we are waiting for about 7 to get sanctioned. There are rejections and many other things happen, and a long review process, etc. And this speaks about the importance of this particular course and also the meticulous arrangement of the sessions in 2 weeks. And also we have conducted these GYAN programs in number of phases from the Center for Educational Technology. The GYAN global initiative of the networking, which is very important for engaging international experts in participating in the leveraging the Indian scientific and technological intervention, where the development aspects will take place through good collaboration from the international experts. This particular GYAN program, GYAN in Sanskrit is called wisdom or knowledge, which actually provides a good platform for Indian students, scientists and everybody to participate and get engaged in scientific discussions, and we'll come to know the global perspective of certain topic. That is the best part, and which is the initiative of Ministry of Education. We are in currently the phase 4. The advantage of this GYAN program is that there are a number of participants who also joined online. We have to stream these programs, stream these sessions. So currently the streaming is also taking place, and audience can join from anywhere, and these recordings can be converted as NPTEL courses. So the NPTEL courses, you must be knowing that there are a number of courses currently available on YouTube for freely available. Also, if you want to get a credit out of it, and you need to register and also write exam to get the credits or certificate, and certificates can be converted to credits. This GYAN program, the 2 weeks or 1 week, that can be converted to, in fact, NPTEL. So this program also is hoping that we will convert to NPTEL later on. From IIT Guwahati alone, the CET, Center for Educational Technology, has developed 700 courses, and they're all up on YouTube. And this is a great initiative, and we are hoping that this will be a very successful program, and I hope we will have a lot of learning that happens, and thank you so much.
Thank you, Bharat sir, for the brief about the program and the activities of the center. Now, may I request Professor Samantamani Hajarika, Head Department of Mechanical Engineering, IIT Guwahati, to say a few lines. Please, sir.
Esteemed Professor Marcus, Professor Nandi, Bharat and Professor Sahu, and dear participants, it's indeed a great privilege to be here this morning and be present for the GYAN course on combustion theory and applications. We at the Department of Mechanical Engineering, IIT Guwahati, we strive to balance fundamental areas of engineering together with very emerging technologies. So this course is a result of that effort, and I'm pretty sure that you'd gain a lot from your interaction here. But beyond this course, I would urge you to explore the possibility of interactions with other faculty in the department or in the institute and make the most of it once you're here. I, on my personal behalf and on behalf of the Department of Mechanical Engineering, welcome you all and wish you a very fruitful interaction in the days ahead that you spend here. Thank you very much.
Thank you, sir. Now, may I request Professor Sukumar Nandi, Dean of Administration, IIT Guwahati, to say a few lines about the program and the institute. Please, sir.
Very good morning to all of you. my colleague on dais, Professor Hazarika, Professor Sahu, Professor Bharat, and the esteemed guest in this program, Professor Marcus, and all of you participants online or in presence. I welcome you all to this program. It is my privilege to be here. The first program, after a long time I am here. It is a little bit emotional because CET started with me in long time back, and this e-classroom, then the other things, initial creations, I was involved as CET head, and that time we were participating NPTEL course, the first set of NPTEL or NPTEL, whatever you can say, that course creations. I was NPTEL coordinator and head of CET, and we got these two buildings. This building, 2 floors, we have to do something. We are struggling to create our courses because we are not having any video recording facility, that to be created and all these things. Subsequently, things came up and we remodeled it, and now you can see we are in a good shape as far as recording is concerned, as far as delivery is concerned, as far as streaming is concerned, every aspect we have grown. So, be it emotional here, but it's nice to see the things are in place. And during this period of journey, since 2004, lot of things happen in this CET at per se, and we have done lot of contributions in national level as well as international level. This is one of them. Coming to IIT is the 6th IIT, and in the series, the first indigenous development of IIT and creation of the IIT. Why I told indigenous? Because no foreign participants. Earlier 5 IITs, foreign participants were there. They helped a lot. This was creation our own. And subsequently, the other IIT came up. And till now, our IIT, we have lots of activities we are doing, considering the interdisciplinary nature, lots of interdisciplinary programs we have started. Today's program, I put it in the interdisciplinary nature because this needs chemical engineering, mechanical engineering, energy science and engineering, and so on, including today if you go to the combustions and other things, people say that Bow combustion is doing some things and used in some places. The feedback mechanism and others comes there also, some electronics and computer science comes in picture. And AI and machine learning is everywhere because we learn the several things, the modeling. Today everything can be done in the simulation level, and lot of labs as well as classes. This course is also part of that. So it is amalgamations of several engineering plus material science. I am putting material science is also very important because this things also from where we will get what and others is also important. Now today's scenario, earlier combustions and present combustions are huge difference. Because today we cannot think of the earlier technology, earlier combustion mechanism, be simple combustions in our house to the nuclear combustions or some other combustions. Altogether, it's the scale is different, the requirement is different also, and as a result, we should learn, we have to survive. Fossil fuel may not remain in long run, we have to survive, and how to use minimum fossil fuel to make it at more available for our future generations. So combustion theory and applications needs to be relook into it, and the guest here, the esteemed Professor Marcus and our other colleagues who will look into this, and you got opportunity to learn. Please utilize the options, interact with everyone. Also, you have to remember that among the participant online or offline, the in presence, this interaction is more important than one-way traffic. One-way traffic never gives learning complete. Why? Because the lecture, what is going on, the person thinking you are getting and trying to explain most of the things own way, but it may not reach to your mind. Your cognitions is another important requirement. So you should learn in a better way. One of you ask questions or interact were benefit to all. But our nature is that better not to ask. But I request you, please interact. You will learn a lot. It's not required to go by theory one way or lab one way, just experiment given you are doing the lab. Learn as much as possible so that you can recreate yourself the such scenarios. So hope this 10 days, no? 10 days you will learn lot about this. It is our need because we are doing fossil fuel, we are using alternate fuel, we are using alternate other options, renewable energy, how to combine them and make it more affordable for the everyone and success in our future generations. Hope you will enjoy this and expect something from this also in future. You people can be utilize this for our Indian need. With this, I thank you all for coming and attending and participating in this program. Thank you.
Thank you, sir, for the encouraging speech. Now, may I request the foreign faculty, Professor Detlef Marcus, Head of Department PTP Braunschweig, Germany, to say a few lines. Please, sir.
So, dear professors, dear participants, so first of all, I have to thank Professor Sahu for organizing this course. It's my pleasure to be here. It's my second visit of IIT Guwahati, as explained before. And of course, the question is, why are we offering this lecture here? So one of the most important topics in our days is global warming. And global warming is directly related to the amount of carbon dioxide in the atmosphere. And this, of course, is related to the use of fossil fuels, as explained from the other professors before. And if we want to stop global warming and to stop the local climate change we face in different areas in the world, heavy rain in Germany or very hot summers here in India, we have to change our energy system. And here we do not have to replace only fossil fuels, we have to use other modern energy carriers, hydrogen-based energy carriers, ammonia, maybe iron. And with this, we have to consider efficiency and we have to consider safety. And both of these topics are related to the work of my institute, or the institute where I'm working, the Physikalisch-Technische Bundesanstalt, the National Meteorological Institute of Germany, and therefore I'm really happy to be here and to discuss with you in 10 days some of the new modern applications of combustion. Thank you.
Thank you, sir. Now may I request Professor Niranjan Sahu to deliver the vote of thanks. Please, sir.
So at the bottom of my heart, I thank to all the distinguished guests who has come here by spend with their valuable times. Professor Nandi, thank you, sir. Professor Hazarika, thank you, sir. Professor Bharat, thank you, sir. And also Professor Marcus, who was visited all the way from different country, Germany, to us. At the same time, I also give my sincere thanks to entire CET team for arranging this or planning for this course. From the last 2-3 months, we have been struggling to get the things done at various levels, especially Kaushik, Mr. Debjyoti, Mr. Kallal, and so many other staffs. And in the end, it is the participants who make this course success. So I wish all of you you will get this course benefited. And thank you for your valuable time, and thank you very much for this inaugural session.
With this, we come to the end of today's inaugural function. Thank you all. I request everyone to proceed towards the tea lawns for tea. Please.
So anyway, good morning to all of you. Okay. So before I start our lectures, let me tell you the background. What is the expectations? What are the things that are going to come out? How you people are going to get benefited in a kind of win-win model situations, which is beneficial for you, for us, and that way. So as far as this course is concerned, take it as if you are taking it any conventional course during your classroom. Don't think that it is a very high level course. It is and how you can get benefited based on the outcome for this course. So the entire intention for this course is that just to give you the brief insight about the basic theory and what are the innovations or the things that is the need of the hour. So for the time being, what my part of the lecture, I will try to keep more or less conceptual things about this course, which is mainly on combustions. Many of the stops, they are available in the textbooks, as well as you can find in this line. There may be many courses which are available online through NPTEL platform. But the other side of the story of this course is that how you can get maximum outcome from our interaction with our foreign expert, which is Professor Marcus, because he works in the area where the combustion with a new technology, that is the demand of the hour or need of the hour, and how you people can train yourselves just to get out of the conventional method of combustions to higher end or the next generation combustions. Last 100 years, the when you deal with this combustion process, we never bother about pollution, emissions, because hardly you will find one or two few vehicles running in the ground, and there are very limited applications where the combustion was fossil fuel was the need. But over last 100 years, the transport sector has grown to such a level that we reach in a situation that we say that fossil fuel combustion is no longer a standalone technology for futures. So we have to go for the future generation methods where we can run our systems, energy sectors, without intervention of degradation of environment, without intervention of pollutions, air pollutions, without intervention of cutting woods, trees, all these things. So this is a kind of a need of the hour, and another big issue of this combustion is because all fossil fuel combustions are carbon based, and when there is a carbon, obviously, and our classical stuffs have already demonstrated or already proved that we are end up with NOx, we are end up with CO emissions, and we are, because of these emissions, there is a detrimental effect of our pollution effects across the globe. Okay, this is the background of this course, and what we have planned is that will, for most of my lectures will be based on the standard conventional theory. I will try to give some insight what research can be done on this particular area, what are the different level of research that we can think of. Some of the things which are already available in the textbooks, but still we do not pay attention because it is not in our course curriculum. So, some of the things also little bit of mathematics involved, where you need the analytical modeling of combustions. So, this so that way the lectures are designed and planned, and Professor Marcus' lecture will be mainly on the hands-on practices with various of mainly with combustion modeling packages like Cantera and other things. Other thing is that this is similar to a kind of CFD normally we call in fluid mechanics term. But all these fluid mechanics packages, they cannot handle combustion modeling, and some people also look for the high end combustions, where we talk about dissociation effects that comes in the area of rarefied gas dynamics, where dissociation effects comes in, where that is normally used in the ramjet and scramjet engines of aircraft engines. So, those kind of concepts, there is no standard technology or standard modeling is involved. So, the aspects are like this: we start with some analytical modeling and end up using some standard packages, then later part we move on to experimental data. In the experimental data, diagnostics also plays a very crucial role. What are the measurements you are going to make? Is it doable? That is the another chance. If doable, what are the instruments that is available? All these sorts of questions you need to ask yourself to perform the experiments. And the combustion experiments are such that you deal with a kind of the situation could be a controlled combustion or uncontrolled combustions. Uncontrolled combustions create a very unavoidable situations, but if you can do controlled combustions, it can do miracle. Means like we in the transport sector, when you travel faster, ramjet, scramjet engines, they are like a supersonic mode of combustions. So, that way you can travel at almost 5-6 times of maybe 12 times Mach 12, 10, 12 Mach number you can achieve for your vehicle. So, it starts with wood burning and there is no end, but till now we have reached to a level of rocket combustions. So, this is the broad domain, and in this domain we are catering so many things, starting from analytics to modeling to the experiments. So, that way if you look at your course schedule, we have designed all about close to 28 to 30 lectures. Additionally, there will be some tutorial sessions. So, we will try to see how best we can go ahead with that. So, in the first lecture, it has nothing to do with the word combustions, rather to start combustion, what background exercise or background topics you need to look at. One thing anyway you have to do the thermodynamics. So here I will talk about the some glimpses or terms that are associated with thermodynamic concepts and all. So it starts with basic thermodynamic modeling, then zeroth law. Then when you talk about thermodynamics things, we have to see that the system has to be defined, that we call as a hydrostatic systems. It is a simple compressible systems. So hydrostatic word comes into picture. It's a hydrostatic is a broad word which includes liquid plus gases, but when you move it to compressible systems, then it becomes only gas. Then the thermodynamics also deals with energy interactions from variety of sources. With thermodynamic viewpoint, we talk either in terms of work or heat. So those form of energy interactions, we call this as a modes of heat transfer. Then we have this to deal with thermodynamic system very closely, or if you can model in a quantitative manner, then you have to define the systems in a quasi-static process, which is the infinitely, which has to undertake with its slowness. Then we dealt with laws of thermodynamics, then Carnot cycle, reverse Carnot cycle, and based on this we come up with temperature scales, where how the Kelvin scale was evolved over the entire history. Laws of thermodynamics also gives variety of thermodynamic parameters, properties, and one such property is entropy, which plays key role whether a system is reversible or irreversible. That is what the entropy word comes into picture. Now, having said this, when we have entropy, then another term that drops in exergy and second law efficiency, which basically talks about any source of energy which what you have, what is its corresponding work potential. Okay. Now, this particular entropy and exergy term actually is very vital for all kinds of combustion modeling. Probably down the lectures, when you see, you will find the definition of entropy based on chemical terms. So main system that we look for when you deal with this, the term, the significant term that we come across in this thermodynamic course, that will be actually used in their applications. One basic things in the thermodynamic system is that, for example, when you, for example, for in a simple analyzing a simple systems, two gases mix or two fluids mix, then it gives the third systems. So when you analyze this as a mixture, we know what is in, what is out, and we have all the parameters known to us in the beginning. But when you do the combustions, because you do not land up in having them same mixture is out, because we have a fuel and we have air, but at the end of the day none of this thing is there in the output, because it has died down in terms of some combustion products. So quantification of each term is dependent on the main source, whereas the common conventional mixture, it is not that, because mixture when it comes out, it has same identity, some identity which is in the in which it gets mixed, but there is no identity when it turns out to the combustion products. So while modeling, either in numerical modeling or experimental things, the cause and effect things comes into picture here, because effects are because of certain input, but that input you might be knowing, but that does not give the some identity which is remains with that input. So that way the combustion products what it will come, you don't have any knowledge of that. So that way the calculation of entropy is and exergy is very vital, because we don't have any identity of main input. And then we have the second law efficiency. So to have effective combustions, quantification of this term is essentially a main requirement. So to give the introduction of these things, and this is something like basic knowledge, that we have some kind of systems, we have some kind of system like this, where we talk about three methods of energy conversion: electrical to mechanical and vice versa, electrical to thermal and thermal to mechanical. So that way things can happen, but to make these things happen, we require the energy sources starting from solar, geothermal, chemical, nuclear, hydro, all these things take part. Now when for combustions, our main attention remains with this chemical fuel, and that is one part of energy interactions that we have to make. Means our main focus would be on this, mainly from the fossil fuel combustions. Other parts are kind of a visualization of next generation combustion, we call as a green combustions. It could be, many people call this nuclear, hydro, solar. They are harnessing energy from renewable sources to get the benefit out of in terms of electrical power or mechanical power. But at the end of the day, our main output is electrical, and we can get the conversion of mechanical output in terms of soft power by running a vehicle, in terms of household applications, it can be electrical, it can be cooking, so many varieties. So that way linking of this activity is very important. Now coming to the basic terminology, I don't have to say many things, because they are textbook stuffs. We have system, surroundings, and when you model this, we call this as universe. And the system, while talking about system and surroundings, the thermodynamic viewpoint says that either it has to be a macroscopic approach or microscopic approach. Macroscopic approach takes as a whole, which normally we deal with analyzing thermal systems. Microscopic approach becomes very significant when you deal with combustions, particularly to the case when you go for reaction modeling, where species try to dissociate. For example, at maybe 800 to 1000 degree Kelvin, nitrogen starts dissociating. Close to 4000 Kelvin, oxygen starts dissociating. And maybe if you go to 8000, 10,000 Kelvin, we will have, during this period also, we have NOx formation, carbon monoxide formations. But if you still go ahead, then we land off having further dissociations at molecular level, atomic level, then atoms becomes ions, ionic level. So all sorts of things that comes into picture, where macroscopic analysis of thermodynamics has no role, and we have to deal with in the angle of microscopic approach, talking about species, atomic level, species formation as a whole. So this is what we say new generation combustion modeling. And talking about this, we have systems, we have closed systems, open systems. Closed system says that there is no mass, no energy interactions, but energy interaction is possible. But when you deal with the open systems, both mass and energy interactions is possible. Now moving further, the evolution starts with the zeroth law, and when you talk about zeroth law, it talks about thermal equilibrium. There we start off the words using the diathermic wall or adiabatic wall. Adiabatic wall says that adiabatic wall means the no transfer of energy in the form of heat with others, which means system does not allow to get into equilibrium, because suppose you have system A, B, C, we have a diathermic wall in between A and B. So, that means there are possibilities that energy interaction can happen in both ways, but if you have an adiabatic wall, this and this cannot be interacted, and this A and C cannot be interacted. Similarly, B and C we cannot interact. So, system C can never be in equilibrium with A and B. So, with that concept we call it that the word thermodynamic equilibrium comes into picture, where the zeroth law says that if two systems are in thermal equilibrium, then it will also be equilibrium with third systems, unless and until they are separated by as long as they are separated by a diathermic wall. The word zeroth law has some historical significance. It has evolved after the first law. So, during that, so that is the main purpose that it was told as zeroth law. Then moving to the analyzing thermodynamic systems, initially we call this as a hydrostatic systems, which takes care about liquid as well as gas while modeling, but we can bring down to a level where if you take particularly for ideal gas situations, gas modeling, then you can call this as a compressible systems, where three different parameters, pressure, density or volume and temperatures, they comes into picture, and all of them has to be kept in some thermodynamic coordinate systems. Here I have put this x and y, x dot, y dash, just to give that it can be of any x and y, they can be of any thermodynamic property. Then coming back to modeling of these thermodynamic systems, if you look at the mathematical representations, for the time being let us say that we have three parameters: pressure, temperature, density or specific volume. They have to be related mathematically. Then what we can write is that, let us say volume, it can be pressure, function of temperature and pressure, or if a temperature, it can be represented as a pressure and volume, and if this is the functional relationship, we can come out of in terms of mathematically in terms of partial derivatives. Through this expression we can find dV change in the volume, we can also find dt change in the pressure. How do you measure this mathematically? Keeping one parameter constant, we try to measure. So, this is the mathematical way of representations. So, these two equations we are using. Now, here we have to see, then we have to see whether our system is in liquid or gas. Accordingly, we can play with these parameters. Is there any change for because for liquids we require two parameters, either pressure or volume, because they are interrelated, but gas we have to define three parameters simultaneously. So, that way the understanding of our or representation of these equations has to be changed. So, this is exactly what we are going to do for our writing the combustion equations in the analytical equations during our combustion analysis. And while talking about hydrostatic systems, we define the terms which is actually the properties of the medium or the gas or liquid that we are going to say. One is volume expansivity, isothermal bulk modulus and isothermal compressibility, then volume expansivity and isothermal compressibility. What it says that it actually by definition you can read it out, but what I am trying to say is that these terms which is like beta or kappa k, and there is another term which is relation k and b, they are reciprocals. So this, if you look at these equations, let us say we talk about beta. Beta stands as volume expansivity. It talks about change in the volume with respect to change in the temperature, keeping pressure constant for a given working given fluid, and that way we define beta. Then we have this isothermal compressibility kappa, which is K, isothermal compressibility K, which is defined by 1 by B. So that way we can modeling it, and here as I told, if it is a these two terms allows you to, these are the fixed properties of the material or the fluid, but these two properties will tell you change in the pressure with respect to change in the temperatures. This just to give you a glimpse that there are mathematical formulas that do exist which can give you the correct information of your in finding the properties. Then we move on to the classical definition of modes of energy transfer. Either we call this as a work or heat. When you say work, it means that we view these systems to be rising and falling a mass against gravity. So it could be electrical work, it could be a any form of energy interactions. It can be electrical energy, it can be magnetic energy, it can be any nuclear energy. But when you actually thermodynamic viewpoint, when you call this as a work transfer, it can be visualized in a sense that we can raise or fall a certain mass against with respect to gravity. And if you cannot interpret as it work, then you have to interpret in terms of heat. So if it is a heat, there has to be a temperature difference. So that way the evolution of heat and work comes into pictures. Then coming to the heat transfer has three main sources. One is conduction, convection and radiations. Conduction's laws are governed by, conduction mode is mainly solid medium, it is governed by the Fourier law. Convection and radiations, convection mode is liquid and gas medium, and radiation will be gas and vacuum. So accordingly these are three laws of convection, three laws. One is Fourier law, second is heat convection, and third equation is Kirchhoff's law, Stefan-Boltzmann's law for radiation. And these radiation terms becomes significant amount which we say energy interactions when you go in the areas of high-end combustions, where temperature you can expect more than 8000 or 10,000 Kelvin, where dissociation effects or rarefied gas dynamics effects come into picture. But in our conventional practice, at lower temperatures, we enter into either combustion or convection. Then coming to the quasi-static process and work transfer, to analyze the work transfer, we have to define a system, and its system has to be specified either in variety ways. One is isotherm with by giving some name into that process, either isothermal, adiabatic, reversible adiabatic, constant volume process, constant pressure process, and they can be of traced in a pressure volume coordinates, in which work transfer is possible through this integral. That is most important. That means we can, once you define this path, we can actually integrate this pressure volume diagram to get the work transfer. So, these are the standard expressions for variety of work transfer in various processes, starting from isobaric, isoporic, isothermal, adiabatic and polytropic. Now, coming back to the laws of thermodynamics, and having said that work and heat, these are the two modes of interactions, and if you take a audit of it in a given systems, if you can actually say whatever form of energy that system interacts, we can put in that gross domain of work transfer or heat transfer, but then whatever, either it can enter into the system, it can go out of the system. So, if you take a stock of it, what is coming, how much coming and how much going, not necessarily that both should match. Now, if it matches, that is well and good. If it does not match, then how do you quantify it? So, that is the reason the term the difference between heat and work was proved to be the fact. It gives a term which is UF and UI. U stands as internal energy, which is initially at the when the system is at the beginning, and final state we say F, and they, for an hydrostatic equations, heat, work and internal energy, they fit a relations. And again with same mathematical notations, the internal energy U we express in terms of the other parameters as well. It can be related with a temperature volume or temperature pressure. So, based on this we say that whether the system is a closed systems or open systems, and when it is a open systems, we define the term enthalpy, when it is a closed system as a flow energy, and when it is a closed system, it is the internal energy within the system, which is internal energy. Then coming back to this is about the overview of first law, and coming back to the second law, there are few silent features of this second law that many books talk about. Now, when you talk about energy, either heat or work, the first law does not talk about the word heat or work, it talks about the quantity, whether 10 kilojoule, 20 kilojoule, whether 10 kilojoule of work or 20 kilojoule of heat. It does not use the word, you just take a stock of energy auditing, just a balance and difference between these two, it gives the in the form of internal energy. But when you come to the second law, it really quantifies, and why we say it is a work and why it is called this as a heat. So, that way quality of the energy comes into picture. Now, come another important significance for this second law is that either work or heat, one can think of the conversion of work to heat or heat to work. So, question arises whether 10 kilojoule of heat can get converted to 10 kilojoule of work, is it possible, or reverse 10 kilojoule of work to 10 kilojoule of heat, is it possible. So, all these questions were answered. That way the energy transfers were categorized in two forms, one is high grade or low grade, and work is always treated to be high grade and heat is taken to be low grade. So, what it says is that complete conversion of high grade to low grade is possible, low to high is not possible. This is one thing, and if it has to be converted, then what is the mechanism that we have to evolve. So, this is one way of answering the second law. Another point is that, and if it is converted, what is the upper limit? How much percentage of work that can be converted? So, all these answers were taken into account. And third most important aspect is a kind of a energy dispersions or energy spreading, or we say that can you localizely store energy on its own at one particular locations. For example, if you put water at, maybe water always flow from high elevation to lower on its own without any constraints, but its reverse does not work out, because that is the law of nature, that is the that way we say that localized concentration constant energy has no value and it has to spread. So, the spreading when it spreads, its own identity is always lost. So, and that spreading, because of this spreading, the thermodynamic gives a term which is called as irreversibility. And this irreversibility is further linked to entropy. How do you quantify this irreversibility? In terms of entropy. And another point is that when you deal with first law and second law, one thing we say, the entire analysis is based on the system and system within the systems, whether the process is reversible, irreversible, and we normally do not bother about what is happening into this immediate surroundings. For example, if there is a burning of fire, in this immediate surrounding you can feel its effect, but to the down the line some other location you may not feel that effect. That is because because it does not have that intensity to propagate further, which means that is the word we call, the term is exergy. So, the word exergy says that when you analyze a systems, you take its advantage, you take its effect with respect to its surroundings, and when you take about this, analyze the system with respect to surroundings, then you have to quantify in terms of exergy. So, there are modeling of exergy which is already there, and here that those things are not direct relevance to our course. One is like a heat engines, which says that how if there is a mechanism of energy transfer from heat to work. So, you have to use this concept of heat engines, which is a cyclic device which has to work in a manner, it takes heat from a high temperature source and it has to reject to give certain amount of work. So, this is what the mechanism of getting work or getting a high grade energy from a low grade source. The other side, if the work gets consumed, we can say either we get the cooling effect. The cooling effect can be of refrigerator or heat pump mode, and these are the some statements of second law statements based on the Kelvin-Planck statement, which is with respect to heat engines, which says that it is impossible for a device that operates in a cycle to receive heat from the single reservoir and produce net amount of work. And the Other side of the second law statement is on Kelvin statement, which says that it is impossible to construct a device that operates in a cycle and produces no effect other than heat transfer from lower temperature to higher temperature. So, this is about heat pump and refrigerator. Then something on Carnot's and reverse Carnot cycle. So, for the second law was evolved with a viewpoint that how do you define a that heat that cycle, either heat pump cycle or refrigeration cycle, in such a way that what are the thermodynamic processes that needs to be involved. So, we have a reversible isothermal process expansion, reversible adiabatic expansion, reversible isothermal compression and adiabatic reversible adiabatic compression. So, compression works means it takes as some work is taken as input, expansion stands as work as output, and the reverse mechanism we call this as a Carnot refrigeration cycle. So, based on that we can draw pressure volume and temperature entropy diagrams. So, that way we can quantify how much heat or how much work transfer that takes place. And these are the some terms, parameter terms. We talks about the quantification of Carnot and reverse Carnot cycle for heat engine and refrigerator or heat pump. And another significant inference that Carnot cycle gives is about definition of a new scale. So, prior to this, whatever thermodynamic scales we are using, either it is a 10 centigrade or Fahrenheit, and the measurement of those temperature value based on the kind of based on the kind of fluid which actually measures the temperatures. So, here we use the word it gives a another scale, we call this as a Kelvin or Rankine scale, and here the measurement is based on this Q and T, and in between there is a functionality that relates. That functionality happens to be a linear function, and as long as this temperature is expressed in a Kelvin scale, we can directly relate Q and T by this linear equations. This is another significant development that we come across. Further, it gives the definition of absolute zero. So, if I say 0 degree centigrades, it is a freezing point of water, and that freezing point was treated as a benchmark or reference, but below that it is possible -2, -5, -20 degree centigrade is possible, but there is no concept of minus 10 Kelvin, because that is the thermodynamic limit that puts. So, absolute zero till date it is not reachable, at least with our planet being the reference, and when you have absolute zero, it gives a kind of a means there is no disorderness in the systems, there is all the molecules become standstill and there is no kind of energy interactions, either work or heat is possible. So, it is a completely static or steady systems. So, what he says, if that is the case, that point of absolute zero, entropy vanishes. There is no definition of entropy at absolute zero. Okay. So, to quantify this, we have there are different to quantify the irreversible nature of a given systems. We have to do in kind of some kind of modeling. What we talk about, one is thermodynamic equilibrium of chemical systems, other is how to include the dissipative effects, and these two terms are very vital when you actually do the chemical reactions during a combustion process. So, these two are going to be used in our combustion systems. So, this entropy word I have told so many things that how the entropy is a very classical term, but it has a thermodynamic viewpoint says that entropy of system always increases, and further when you talk about chemical reactions, so reaction has to proceed in the direction of increasing the entropy, which means that is the only parameter through which you can judge a chemical reactions, because of your fuel we have air, and then when they mix together you find their initial entropy, and if at all there is to be combustion products, to down the combustion products when you actually calculate their entropy, you must see that entropy should be higher when the reaction proceeds. So, that is the direction of increase in the entropy, or entropy generation is also a measure of irreversibility of a given process. So, these are the some classical expressions. If the process is a reversible process, we say in a solid line. If the same process is defined from an irreversible manner, it is shown as a dotted line. System goes from 1 to 2 in one direction, and system comes from 1 to 2, and when you say reversible, which means that when we have initial state 1, we can go to 2 in a reversible path, and if you also there is a possibility that we can come from 2 to 1. But when such a system is defined in an irreversible path, one way direction is possible, reverse is not possible. So, that way we come up with the equation called as Clausius inequality, and it gives the fact that entropy of an isolated system always increases. And for irreversible path, we have this term which actually quantifies the what is the entropy generation. These are some of the equations that are used to calculate the entropy for a gaseous systems. Talking about using the gas equations, ideal gas equation PV is equal to RT, one can find the change in the entropy from its state coordinates, either temperature volume or temperature pressures. Now, coming back to another significant term, when we say exergy, which actually quantifies what is the work potential of energy. So, if you have a systems which is quantified as a total energy, this total energy can have multiple parts either in the form of work or heat, but actually when you see for these systems, exergy potential is only certain portion. That means, if you say 10 kilojoule of energy which is constrained in a systems, its exergy potential cannot be 10 kilojoule, it has to be less than that. Now, when you do this and that less than that is not because of our system issues, it is mainly because the nature of energy has to dissipate, which is not recoverable. So, we call this as a unavailable energy, which is due to irreversibility in our nature. So, whatever most efficient system if you do, even then there will be some energy which is not recoverable. Now, this energy, how it enters to a system, it can be come from mass, heat or work, and each will have its work corresponding exergy potential. So, exergy can, that means in other word we say exergy can come through mass, it can come through heat or it can come through work, but each will have when it goes out, it will have its corresponding exergy output. So, that way the total energy never matches here. So, in that sense we can change is that is the exergy change for the system and which is exergy destroyed. And this exergy destroyed is nothing but your unavailable energy. So, this is how you link the overall, this gives the when you in many systems in our research study we do particularly in the when you deal with engine analysis, we talk about energy analysis, but it is better that if you do exergy analysis, because that will give you the real picture by analyzing the complete thermodynamic viewpoint in terms of energy which is getting wasted from the system. So, this is what something like that, how do you calculate this exergy. So, you have for closed systems we call this as non-flow exergy, for open systems we have flow exergy. So, exergy from mass, heat and work, we will have expressions. So, they can be found out keeping surroundings into pictures. How that surrounding, so exergy destroyed, why it comes? Exergy destroyed means entropy increase. So, if you look at this term in both the equations, either non-flow or flow exergy, there is a term exergy which is destroyed, which is defined by T0 into S2 minus S1, and here also same thing, same term appears in both the expressions. So, T0 stands for the surrounding temperature and S2 always increases. So, these two terms is always a positive quantity, which means that even though you are calculating exergy, this term takes away some part of it. So, that is the reason exergy destroys. And based on these laws are formed with respect to exergy reversible process, there is no exergy destroyed, irreversible process and impossible process. For any system natural occurring processes, we need to have destruction of exergy, and we cannot claim any processes which for which exergy is destroyed is less than 0. And this is one way that to quantify another term that comes in. One is efficiency, what we define while talking about heat engines based on this either Carnot cycle efficiency or in terms of heat transfer. Here it is mentioned in terms of heat transfer. So, there are three parameters involved here. One is best with respect to these heats, one is Q1, Qs and Qu. Qs enters to the systems, Qu which is actually utilized, Q1 goes to the surroundings, and this surrounding town number it depends, and if you actually calculate what is the Q in terms of the expression from the Carnot cycle, this turns out to be this. That means, when you talk about exergetic efficiency, work potential of this Q u is here, work potential of Qs is here. These expressions are nothing but we get the relations from the Carnot cycle, and finally it turns out to be exergetic efficiency in terms of the system efficiency. So, these two things are correlated, which says that exergetic efficiency is always also lesser than the your efficiency of the system, which is the conventional, the way the efficiency are defined for heat engines. Normally, this exergy efficiency we also called as second law efficiency. And finally, I just want to give some emphasize a realistic work, some kind of a comparison how you view exergy and energy in a manner. For example, when you if you look at only this part, it is some kind of arbitrary systems in which some energy in terms of heat enters and some energy in terms of work it produces, system produces, and while doing this some mass flow which is entering and is carrying some energy into it, and something mass flow that takes out some heat. So, what the significant term, I just kept some numbers, is that suppose it is 90 which is entering in terms of Q, flow and energy which is entering into the systems either through kinetic energy, potential energy or enthalpy or flow work, which is 10. So, total entering is 90 plus 10, 100, and here also you have here 40 and your work output give you 60. So, if it is a completely first law analysis, the energy auditing comes into picture 100 and 100. Now, even though you introduce internal reversibility within these systems, this 100 kilowatt could be lesser than that. So, that is based on the first law and second law analysis. But when you represent in terms of exergy, and even though and to make your system efficient completely, if it is 100% efficient, we will have 100 kilowatt work. I mean energy auditing we can achieve by introducing RGF, that system does the you use the system to work in a manner that it is a very small process, steady processes without involving all the instruments or mechanisms or devices. They work in a very efficient manner, which is doable with 100% efficiency. But still then, if there are some internal irreversibility comes into picture, for example isentropic efficiency for compressor, turbines, if you define those things, it will be little bit lesser than that. So, whatever may be, this is the energy auditing or balance between from the first law and second law. But when you actually convert their work potential to exergy analysis, you will find that although you are giving 90 kilowatt of work heat entering into the systems, its exergy potential is actually 60. If you have shown you the equations, you can calculate. You can be always less than that, because that term T0 into S2 minus S1, and for each term there will have exergy potential of enthalpy, exergy potential of this E which comes into picture, EFE which is comes out of this thing. If you take out its exergy potential, although it is 10, it is actually it could be less than that too. And even though through this process, and of course one thing is sure, since it is a work, its corresponding exergy potential will be same for this thing, because it is a work. So, these two remaining same for both the cases, and if we recalculate the same term in terms of exergy, you will land off an analysis called as exergy analysis, which says that exergy destroyed, there will be always exergy destructions, and that can be quantification. Why it is required? Because exergy analysis is very vital for any kind of analysis, thermodynamic modeling analysis for any kind of system. Okay. So, these are the some of the things that I need to talk about, and of course, in these lecture notes there are some problems which I need not have to describe explicitly I have to talk about here. Maybe there are some review questionnaires. When you share these slides to you, you can actually try to revoke or do some analysis understanding for this kind of simple problems, that those things we can take off in these tutorial sessions. These are the some problems. I will try to see if it can be done towards the end of our session. Okay, so this is all about my part, and maybe if you have any questions we can share, or maybe after that we can start our next lecture.